to take this opportunity to introduce our co-host, Professor Riyad Mahdi. Please, thank you.
Thank you very much. Good morning, ladies and gentlemen. Yes, my name is Riyad Mahdi. I'm the director of the Smart Structures Laboratory. What I would like to share with you this morning is the development of the Smart Structures Laboratory, which is a unique facility here at Swinburne. So the Smart Structures Laboratory, as you can see, this is a shot of the two buildings. This is one of the buildings that is here. That's where we are now. And the Smart Structures Laboratory is here. So you can see the lab is right on Burwood Road with a glass facade. Usually, structural engineering laboratories are usually stashed in the back of a building in a shed because of the fact that when we test things, we destroy things, there's a lot of debris, there is a lot of things that need to be, like cleaned up and things like that. But the university made a strategic decision that it wanted this kind of laboratory to be right on Burwood Road with a glass facade in order to engage with the public. And what that really means is that it is a very challenging thing for the lab staff. They have to keep it neat, they have to keep it tidy and busy. A very strong, a very, very unusual or a very difficult combination of things to be satisfied. This is the lab when we first started, about 5 years ago. It doesn't look like that anymore. So what the lab consists of is a strong floor and strong reaction walls. The strong floor is a 1 meter thick, heavily reinforced concrete slab, suspended slab, as well as the walls are also 1 meter thick. This is what the lab looks like now. Not only do we have this exposure to the outside world through the glass facade that you will see, we also project the experiments that we do on a very large screen. So we engage with the public, we engage with our visitors in what we present here, what we test here. This is another shot of the lab that you will see today with demonstration that will be given to you around noontime. One iconic part of the laboratory is the MAST system, the multi-axis system of 6 degrees of freedom combined with hybrid simulation. What this system is, it's a cruciform, almost 1 meter deep cruciform, and you have got here the dimensions of it, almost 5 meters by 5 meters, with a height of 3.5 meters. Just to show you some of the things that we do here with this MAST system. So for example, one of our ex-PhD students, Dr. Scott Menigan, he tested wall panels and shear walls for earthquake resistance using this MAST system. And there's a small video clip here I would like to play for you. Yeah, this one. No, here, click on it. Yeah. So this 6 degree of freedom system is imparting all the displacements and the rotations on this wall. You see the dots here. We use image correlation photogrammetry to trace the displacements of the wall panel. So we run this until we have got full failure and we get the full response of this wall panel. Another one is also by Dr. Scott Menigan, is a cast in situ, what we call shear core. That's the central part of any building that you see in construction. That's also subjected to an earthquake, simulated earthquake. So if you can click on that, Graham, thank you. And you can see the full response of this wall. This is almost like full-scale testing, almost like full-scale testing until we get the full response of the of the shear core. So from this, we learn how to design these things, how to improve the design of these things, particularly when it comes to connections between these short shear cores and the other structural elements in the building. So this 6 degree of freedom system, as you can see here, it has got movements in 3 directions and 3 rotations. And this is a short video clip again that will show you what the movements are like, the individual movements are like. So you have got the Z direction movement, plus minus 250 millimeters. Each of these actuators is 1,000 kilonewton, 1,000 kilonewton in capacity, the vertical ones. And you have got 4 horizontal actuators, 500 kilonewton each, again, plus minus 250 millimeter stroke. So a combination of these can be imparted on a structure that can be placed underneath this cruciform. This is all custom made, and the cruciform was designed here and was constructed here. All the actuators and the control systems are from our co-sponsor of this event, MTS. And this was completed 3.5 years ago. So it's pretty new. It hasn't been in there for a long time. But it's a very, very busy equipment. Let me explain to you here the level of testing that we normally do and the relevance of what we do here in hybrid testing and or hybrid simulation to what is important or what to the integrity of our structural systems. Normally, we do tests on material level, on a component level, whether it's experimental or theoretical. Okay, so at a component level, what you get, you have simulation and you have got physical testing. But what does this have to do with the whole structure? Well, there is some relevance, of course, but that's not the whole structure. So what we need here is that we need to go to a higher level, like at the element level, element component level. You can go up to the upper level of components, so part of a building, part of an aircraft, and so on. Obviously, you cannot test the whole structure. Obviously, you cannot test to destruction the whole structure. That defeats the purpose of building the structure. So here is what hybrid simulation does. It can allow you to test part of a structure that is a critical element and somehow link it to the whole structure through what we call hybrid simulation or finite element simulation. So it's a combination of computer analysis and the physical testing that you are almost there, like you are almost testing the whole structure physically. So this is as good as it gets to testing the full structure, which is it's a very difficult thing to do. So as an example here, and I'm sure my colleagues here are going to talk a lot about this because that's the purpose of this session, hybrid simulation and its applications. So, for example, if you have got a building like this one, and you are going to see a demo of this today. So if you see a building like this one and you want to test it for earthquake simulation, so you select some component of it, subcomponent of the building that is most critical, such as this column, which is the corner column. You can test that physically, whereas the rest of the structure, the rest of the structure sits in the computer, it's simulated, but there is continuous communication between the simulation and the physical testing through that node in here. So basically that's what hybrid simulation is. You can apply the same thing for bridges. So for the most critical element in a bridge would be the pier, the whole structure again in the computer, and the pier is tested physically. Just to give you an idea about the accuracy versus the test cost, this is an illustration only. So when you do a quasi-static cyclic testing of a component of a structure, the accuracy is usually low in terms of its relevance to the total structure, but the cost is very, very small. But if you do the full dynamic testing of the entire structure, which is here, the cost is, the accuracy is 100% accurate because you are testing the whole structure, but the cost is very high. Hybrid simulation is somewhere here. At a slightly higher cost, you can achieve a very close simulation to the entire structure in terms of behavior, in terms of response. The other thing is that it allows you the ability of doing what's known as distributed testing. So you can do different components of structure. You can test them in different laboratories, linked up all together in cyberspace, linked up all together with simulation, and you can achieve that kind of integral testing of a number of components of structures around the world. And that is one of the advantages, one of the main things about hybrid testing is that it allows the testing of more than one component. So for example, this is an example of distributed testing. It doesn't, it's only local, but it doesn't have to be local. So for example, the simulation is here. That's where Javad Hashemi's office is. He does all the hybrid simulation for us, and the testing is happening here. So you can carry out this simulation and physical testing at the same time, and you can achieve, that's an example of distributed testing where you have got one simulation here, the simulation here, and the physical testing here. But if you have another component to be tested somewhere else, that they can all be linked up to this simulation, and you can achieve more information from a structure and structural response. Now, just to give you, this is a simple summary of my colleagues here, the experts in the field, are going to give you much more information about the hard facts and the science behind hybrid testing. That's the purpose of the session. But I would like to show you here is the importance of our Smart Structures Laboratory. We have got more than 20 academic staff use the facility in different types of research. We have got about 50 PhD students, more than 50 PhD students. 25 completed their studies, and 25 are currently doing their PhD work at the lab. And also we have got from other universities, from Melbourne, Monash University, they do their research here. We have got more than 250 undergraduate students use this facility for undergraduate demonstration testing, and we have got more than 50 industry-linked research and consulting jobs, and these are the companies that have been doing work with us in our laboratory. The MAS system has attracted a lot of attention in Australia and overseas. So for example, for research services, a lot of ARC research-funded projects have been using this facility. These ARC, Australian Research Council projects, some of them are Swinburne, some of them are from other universities. We have won 2 major awards on the development of this facility, the W.H. Warren Medal and the Innovation in Research and Development from Engineers Australia. And as I said, it attracted a lot of publicity. We wanted to share with the public, we want to share with the world what this facility does and its importance for engineering research. The story of the building of the Smart Structures Laboratory and the multi-axis substructure testing system has recently been published by Springer Open, and these are my colleagues here, myself and Javad Hashemi, Robin Kalfat, Graham Burnett, and John Wilson. We put together this book, and it's out in fine bookstores if you would like to purchase one. So it tells the whole story of how we build the laboratory, from the construction of the reaction walls and also the strong wall, the strong slab, and the construction of the multi-axis mast system. No laboratory is really going to be run efficiently without the excellent support of our technical staff. And I would like to acknowledge Michael Colton, who is the supervisor, Graham Burnett, who is our senior test engineer, and I'm very thankful to Graham that he has organized this session with our MTS colleagues, and he has done an excellent job in doing that. Kevin Nivarat, our technical officer, and Sanjit Chandra, he is on leave. He couldn't be with us, and Kia Rasiki, another test engineer. Before I finish my presentation, I would like just to let you know that this is part of what is this is part of the Center for Sustainable Infrastructure that we have in our university. The director of the center, Professor Jason Jayan, unfortunately he couldn't be with us because he is at an overseas conference. Jay is building a new facility now. It's the 3D printing, the automated construction facility. So that should be developed by the end of this year. And this facility is going to be right across from the Smart Structures Laboratory. So watch out for this space. There are a lot of developments at Swinburne in the area of civil infrastructure. And with that, we have a short video clip that describes what hybrid testing is. And this, we have developed this for in general, it's not too technical, for the public understanding of what we are trying to do here.
Earthquakes are the largest potential sources of casualties for inhabited areas, leaving cities in disaster and killing tens to hundreds of thousands of people. Damage to structures not only causes loss of human lives and disruption of lifelines, but also long-term impact on the local, regional, and sometimes national and international economies. The reliable prediction of non-linear structural behaviour and the failure mechanism during severe seismic events has proven to be an extremely difficult task. Experimental research is therefore critical towards better understanding and predicting the seismic response of structural components. There are several different experimental techniques that can be used to test the response of structures to verify their seismic performance. One of these is the use of an earthquake shake table, where structures are excited in such a way that they are subjected to conditions representative of true earthquake ground motions. However, due to the expensive costs, complexity, damage to the equipment, and the limitations on the size and capacity of these earthquake simulators, structures are typically tested on a reduced scale or a highly simplified model is used. The scaled and simplified model does not necessarily represent the response of the full-scale structure, which questions the validity of the shake table tests. Hybrid simulation, which is also called the pseudodynamic test method, is an attractive alternative for shake table tests. Hybrid simulation is a hybrid procedure that combines classical experimental techniques with online computer simulation for cost-effective large-scale testing of structures under simulated dynamic earthquake loads. Hybrid simulation facilitates the study of structural response by experimentally testing only the critical portion of the structure, while the rest of the structure is modelled numerically in the computer. At each step of the analysis, the governing equation of motion is solved, similar to pure numerical simulations using a time-stepping integration. The calculated displacement demands are then sent to the lab and applied to the physical specimen using computer-controlled actuators, while the numerical portion is analysed on the computer. The resisting forces, including shear, axial and moment reactions, are measured and fed back to the computation solver to calculate the displacements corresponding to the next time step. This process is repeated until the ground motion is concluded. Multi-axis substructure testing in the Smart Structures Laboratory at Swinburne provides a powerful tool for investigating the effects of earthquakes, hurricanes and other extreme events on large structural components using hybrid simulation testing. A sophisticated 6 degrees of freedom control system is used, utilising 8 high-capacity hydraulic actuators that enables application of complex multi-directional deformation or loading schemes to structural components. In addition, a rigid steel crosshead is used to apply triaxial control, yaw, pitch and roll, to the test structures, and also to apply planar translations to planar substructures. The system features mixed mode control, allowing users to specify the position or force required for the desired direction of loading to test large-scale structural components, including portions of beam column frame systems, walls, tanks and bridge piers. The popularity of hybrid simulation amongst structural engineering researchers has grown to a great extent. Geographically distributed testing is one recent concept that has been developed from the use of substructuring techniques and benefited from technological advances in data transfer and computing. The concept of geographically distributed testing is that individual substructures do not need to be within the same facility, but can be linked by either the internet or other methods of data transfer. Therefore, laboratories with much larger capacities can be used for experimental subassemblies. In terms of the numerical portion of the hybrid simulation, there are also benefits in allowing for the use of more powerful computers or even supercomputing facilities to run the hybrid simulation test, since the computers running the analysis do not need to be in the same laboratory. For example, to evaluate the seismic response of a bridge, a multi-site hybrid simulation can be carried out. The column of the bridge can be tested in a Smart Structures laboratory at Swinburne that is able to perform multi-axis substructure testing, while the pavement of the column can be tested in another facility across the country, and the rest of the structure can be modelled numerically in a facility with supercomputers, for example, the University of California at Berkeley. The multi-axis substructure testing system in the Smart Structures laboratory provides a powerful and cost-effective tool to investigate the dynamic effects of extreme loading events on large-scale structural systems through local or distributed hybrid simulation testing.